Are we ready?
That's rolling.
All right. Good afternoon, everyone. Welcome to our first ANA Distinguished Seminar of the year. It's my pleasure to introduce John Valasek, Professor John Valasek from Texas A&M in their aero department there. I'm going to abbreviate his super long bio. He's been busy in his career. I think it's the short version. He stays engaged on a lot of fronts. So I think you've talked to people today. In your role, you've been the president of Sigma Gamma Tau, very involved in AIAA student chapters. He is going to talk to us about some of his research, which is in multiple timescales nonlinear control. But you also work in hypersonics, UAVs, and everything related to that. Flight controls, broadly speaking. Spent time in industry before getting your PhD. Mm-hmm. And then you've been at Texas A&M ever since, I believe.
25 years.
25 years.
Mm-hmm.
All right. So he has had a number of awards for his work, including the ASCE AIAA John Leland Atwood Award for National Outstanding Aerospace Educator, National Faculty Advisor Award for AIAA. He's written books and is a fellow of the AIAA and a number of other distinguished honors. I'm going to leave it at that and turn things over to you so you can tell us what you've been up to.
Okay, very good. Thank you, Dr. Morganson. What I want to do today is talk to you about this good work that Christy has already given you the title for. So let's go to the, come on. Let's do it that way. There we go. Okay, so the briefing agenda on this, we're going to look at the theory computation experiment paradigm. So the first thing we're going to do is look at standard versus non-standard forms of singular perturbed systems. We're going to look at geometric singular perturbation theory and why we went to that to give us some good advantages. And then we'll talk about state tracking with output feedback. The computation part, I'm just going to give you one little small example to start to see how this works. I'll show an F-18 example, simulation of it maneuvering, and then we're going to go into compare 3 different time scale controllers to be able to see how they can do it. And what I'm going to show is first a state feedback, then we'll do 2 different types of output feedback controllers to compare that. No experiment on this, that's still planned in the future to go to, and then conclusions and future work. So the first thing I want to do is mention about interesting connection with University of Washington, and that is the AIAA Student Paper Conference 1985. So that's when I was an undergraduate student, and we had people all over from Region 6 who are there going, and a person walks up to me, and this is, again, we're like undergraduates, and he walks up to me, and he walks right up to me, and he says, "UW," and I said, "No, me, John." And I said, "In fact, no, I shouldn't say that. I said, I'm John." And he said, "UW." And I said, "Where is this going?" and everything. I couldn't tell where this was. And I just did this. And then he starts unbuttoning his shirt. Okay. And I thought, several things can be going on here. Either A, he's Superman. B, he's going to beat the crap out of me. Or, you know, can go to some kind of bad place. And he unbuttoned his shirt. And here's a big UW that's purple that's on that. And so he's saying, "I'm UW." I said, "Isn't that Washington?" He said, "No, we call it Dub." I said, "I'm UW." And I'm like, okay, so that was my very first exposure to University of Washington. And he had been asking me a very, very important question. We're at the hotel and he was looking for something. You can probably take maybe a guess or not as to what he was looking for and everything. It was a particular location where everybody was at. So I'm thinking, I thought it was Washington the whole time. It's UW to be able to do that. All right, so the first people I want to recognize and thank on this, these are my current version, my student team. We've been actually now, they haven't been, but this is the 25th year of them. And so we got to take this picture last Thursday. So this is a very, very recent picture. This is our 2022, 2023 picture. And I said, "Guys, this is the picture I'm going to show when I go to University of Washington." And they said, "Oh, no, you need to show the picture we want for that." So I acquiesced to them. This is the picture, the good picture that I wanted to show. This is the one they insisted that I showed you guys. So there it is. That's the fun picture. Taken at the same time and everything. So there it is. There's the student research team. And I'm going to attribute a lot of this because it's a team effort, everything that we're doing in there. All right, for the lab, just really briefly to talk about the things that we do. You can see all of those. The things that I want to point out, the two newest ones are quantum control and then cybersecurity. So I'm getting into quantum control because I have a student that is working on that for his dissertation. And he's already got 2 journal publications on that. So that's brand new. He started with me in June. And then the other thing is cybersecurity that's down there. So we've been working on cyber controller acquisitions, which is the nice word for a hack attack on it. And that's to be able to take over UAS. We're not touching GPS at all. This has nothing to do with GPS. This is saying, can I go into the controller? Can I take over the controller and make the system do what I want? And the answer is yes. We've developed the theory on it, have several publications already, and we've been flying it like a lot. And what it does now is something like a modal AI quad-rotated Sentinel. We can fly that now, and it thinks it's going to do a certain set of waypoints, like a rectangle or something. We can go into it and take it over and make it where we go where we want to go. But interestingly, it's the system itself still thinks it's flying its original point, and it's sending back to the ground control station falsified information. So it still thinks it's hitting these 4 points. We're making it go somewhere else entirely that doesn't even know it. So the easy thing about this is the nice thing about it, I should say, is you don't really have to have much information on the controller. You just have to get it on there. So we're not doing the vector to get that on. But once you get that on there, it'll take over the controller. And again, nothing doing with the GPS on that. So that's kind of new. For the field expertise, we've been flying UAS for a lot of years, 23 years, all under FAA there. I've done a lot of flights and a lot of programs and been flying a lot of different vehicles, rotorcraft, fixed wing. That one's a 450 pounder, the powered parafoil. Before I start the presentation formally, that's now our background. I want to recognize somebody. So this is an alumnus of your department. So Dr. Jan Roskin got his PhD in 1965. He passed away 3 weeks ago on his, just after his 92nd birthday. World famous. He has taught airplane design at the University of Kansas since 1966 and taught it internationally. And they said, I guess they put together 11,000 people he has taught airplane design to. A real giant in the field, nice guy. He was on my master's committee and he was on my PhD committee too, as a committee member for doing that. So you guys are very honored to have him as a alumnus. He worked at Boeing at the time and then was getting his PhD after doing that. Okay. So let's talk about some two timescale systems. First, I can have linearly damped oscillators, and those are not too terribly interesting. I can have a flexible beam where I'll have the beam motion as you see theta moving, and then I'll have the tip deflecting. If I go into the aerospace example, now it gets a lot more interesting because I have phugoid on the top, short period on the bottom. So phugoid is going to be a very low frequency, low damp mode, short periods, high frequency, high damp. You're going to see phugoid expressed in velocity and pitch attitude angle. You're going to see short period expressed in angle of attack, and then a body axis pitch rate. So when you're looking at the scales on these, it's a little hard to tell, but you see up on the left there, the vertical goes to 8,000 on phugoid, and this one is like to 80. So you're off by, at least a order of magnitude. Typical short period frequency is going to be about 2.5 radians per second, like for a fighter, and then phugoid is going to be sitting right at around 0.1 to 0.05 for that. So big separation in that. And when you look at the time histories, there it is, the one that's out of a well-known book and everything. So there you see again, velocity keeps going long term, and the short period damps out very, very quickly on that. If we look at this now for the flight control problem, here's the dots are missing. Dang it, that's sigma dot and W dot. So if I have something that's going to be a typical like an F-35 fighter, I'm going to now say that this thing, we're typically going to model it as a fine in the control, and P is just going to be some parameters there. So we can typically model it that as, nonlinear. If I go to something like a morphing vehicle, this is a grid model showing how a wing can morph into different shapes, 10 independent morphing degrees of freedom to be able to do that. Then when I make those assumptions, and I pop through with that, that's not going to work, because for this now, I'm going to have this separated out and it'll be non-affine to the control. And we typically will do high performance aircraft, commercial air transports then in affine and control. So the issues are that I have multiple time scale behavior, like I've shown. It's going to be nonlinear to control to be able to make it work. Real time onboard control and time very unknown dynamics. So the typical things to do are to gain schedule, do offline pre-computed control, and then go after linear system representation. So the two that I'm going to be talking about the most are the timescales and then linear system representations for these. There's a bunch of applications for these. Aggressive maneuvering helicopters have the same kind of problem too. The PCA's propulsion controlled aircraft that NASA had done several years ago and then flight tested, that's using the engines as a primary flight control to steer it for heading and then also in roll for that, and then autonomous soaring. So there's a lot of applications. Okay, the theory to go after this is the following. If I've got a particular system that's going to be X are the slow states, Z are the fast states, and my gosh, that is supposed to be an epsilon, so the character fonts are completely out of whack here. And that is also an epsilon that's right there too. And it's not a dot, that's just epsilons. So I've got slow states, which are X, fast states, which are Z, and then the singular perturbation parameter sits in front of the fast states, and that's going to have a value between 0 and 1. If sigma is going to be 1, then X dot and Z dot are all occurring at the same time scale. If epsilon is going to be much smaller than 1 heading towards 0, now what happens is I take 1 over epsilon, which is 1 over a small number, and on the right-hand side, that's going to be a multiplier that's going to make those dynamics go much faster. And in the limit, if I have infinite separation, will be when epsilon goes to 0. So what you do then is the typical analysis is to say, I'm going to set epsilon equals to 0, get my infinite separation. Now have this is going to be just strictly a function that I have to find the zeros of, and that's still going to be a differential equation. The non-standard singular perturbation model is going to say that I don't have a real root for the fast states, infinite manifolds. You don't have results in the aircraft literature, except this slide's a little old, it's ours that are in there. And finally, Friedman started studying in 2001 a way to regulate that. So here's what it looks like. If you look at the standard systems, one class is where fast dynamics are in the linear and the fast states. You see many, many works going back to 1952. Non-standard is literally saying this: if I have the fast dynamics are also going to be nonlinear, that's when I have non-standard, and that's going to be a lot harder to do that. So Narang Siddharth, who was my PhD student, worked on that with me in 11, 12, and 14. We had some things publishing in that. Okay. And this book, I always point this out, Peter Kokatovich, Hassan Khalil, and John O'Reilly. This is a reprint of an earlier text in with SIAM. This is Singular Perturbation Methods and Control. This is like the primary book that was done. But when Peter Kokatovich and those guys did that at the time, they were doing the standard systems because you can get solutions for it. Research-wise, if we look and see what's been done and not done, here you get to see these two-stage design, asymptotic stabilization, simultaneous tracking of slow and fast, and then output feedback. So Narang Siddharth and I did this in 2012. Saha, who was my other PhD student, did some of that. And notice what's sitting right here. Everybody had been doing full state feedback and nobody had been doing output feedback on this. It's just sitting. And there's still, that one is right there. Simultaneous tracking, slow and fast with multiple isolated routes. So this is showing where there's a need to go after that. And that's what we're doing in this presentation. These are just whacked out. Okay. So these are going to be field. That's field of real numbers. So it's the Cyrillic R that's going to be there. So if I have this system, I have slow system states are going to be X's when you see that. Delta 1s are going to be slow actuator. Z are fast states. Delta 2 are fast actuator states. And the timescale parameter, it's again, epsilon is going to go between 0 and 1. So there's what I have. I have the slow states, the slow control, delta 1 dot, the fast states, and then the fast control. So they're all differential equations. And the objective here is I want to track a reference trajectory as time goes to infinity, pretty standard stuff, to be able to do that. So this is going to be very typical again for aircraft or some other kind of system, spacecraft, where I've got slow and fast actuators. Now, here's where the geometric singular perturbation theory comes together nicely. Fenichel did this in 1979. Everybody looked at Tikhonov because Tikhonov was looking at these to say, if I'm linear in the fast states, I'm going to have real roots I'm going to have roots to these things that exist, and I can just go after and get those roots. And what you do is you're going to take those for Z, solve for Z, because you have 0 equals then. For Z, plug it back up into the slow state equation, and then that's how you're going to get it. Now, if I go to the geometric singular perturbation theory, I'm using manifolds, and it's all about that. This is really nice how this works out. So you see the derivatives with respect to the slow time scale t. I have x1 dot is equal to minus x1 minus z. x2 dot is minus x2 minus z. and that it's epsilon z dot is equal to minus c. If I now create a fast timescale derivative tau, you see that I have on the right there. I don't have to read those to you. But here's what I do for this now. If I substitute epsilon is equal to 0, I have the slow subsystem. Notice what happens now. I have x1 dot is equal to minus x1, x2 dot is equal to minus x2, z is equal to 0. What is this saying? This says that when the slow system is evolving, so when these slow states are evolving, there's the differential equation, how they evolve. The fast states have already gone steady state. That's why z is equal to 0. So you saw the examples I showed earlier. When the fast states are going really quick and then they're gone, the slower is still evolving. So that makes total sense for doing this. When I look at this one on the fast subsystem, now that's x1 dot is 0, x2 dot is equal to 0. So that says that actually right here, the slow state is not even moving yet, but the dynamics for the fast subsystem are moving. So this is like freezing time and saying that the fast subsystem states are moving, but the slow ones are frozen. So this one, slow is frozen, fast is moving. On that one, fast is frozen, slow is moving to be able to do that. And so what you can say then is the slow system will approximate the whole system. This is the geometric version of this, provided the fast subsystem is stable about the manifold. Okay, so what that looks like graphically is this. There's the same two things, the fast and the complete slow subsystems that I have. And what this is just showing you, like it's kind of like a phase portrait, but it's in free space for that. The complete is going to be the blue, the slow subsystem is in the pink, and then the black is going to be the fast subsystem. So that's just showing graphically where it is. The neat thing about that is that if you use this, if you're going to be using the version that Tikhonov did in the 1940s and everybody's using before, you will get to exactly the same result. You just have to have isolated roots. If you use the geometric singular perturbation theory, you get to the exact same equations, but you're using manifolds on there, and using invariant manifolds, you will get to the same thing. Now you're not having to worry about, do I have roots of the fast states, that fast differential equation. So that's the beautiful, that's what allows you to get away from having the fast states be linear, and they can now be nonlinear. So the two-stage composite control has been done for a long time, and you break it into slow and fast. Modified composite control, we did that, and we get bounded tracking from it. Let me say why this sucked, okay? You're having to approximate the manifold. Everything's about the manifold here. So a tremendous amount of time was spent approximating the manifold and then ensuring everything converges to the manifold, okay? So we did that a lot. And then what you really find out is there's a better way, which is what I'm going to show you in a minute, because again, approximating that manifold just took forever. And then there's the approximate tracking, which you just neglect those. Okay, so here's what it boils down to. If I put this into error coordinates, the analytical construction in the manifold is not possible. You can't do it, but you can approximate it with a lot of work. If I have lack of knowledge of that timescale separation parameter, so there are journal papers out there that people have get an entire journal paper to be able to find that value of epsilon for one value. I mean, for aircraft work, this was done about 30 years ago, and people did an entire journal paper to say, using wind tunnel results, at some, flight velocity and everything for that, epsilon has a value of like 0.5. That's an entire journal paper, and they took a ton of time to do that. So it's not practical to be able to get that. And then, of course, not all actuators are fast and slow. So the idea here is to use these reduced order models using singular perturbation theory and include the fast states in the design. One thing I forgot to show, I'm going to go back to this, something that's important here. Notice what I get out of this. I have 30 derivatives. They're up there in the original system. This is now reduced order. I'm always going to get reduced order because no matter how many states that I have that are going to be with differential equations, I'm going to reduce it by 1. That's always going to be 2. So this one does not suffer from cursive dimensionality. I can have a bazillion states, but I'm going to have a bazillion minus 1 when it comes to have to deal with it. So that's a nice thing to do that. Okay. Now, the big idea, if you've seen the VeggieTales, any of the VeggieTales cartoons, you know about the big idea and everything for that. This was inspired by using the Lyapunov-based control, because the way that you can do it is to say, design my controller, now come up with the suitable Lyapunov function, where the Lyapunov function is positive definite, and then the derivative is negative definite. That's great. The other way to do it, which is nicer, is to say, I will define a Lyapunov function and then set up a controller that always maintains that v is positive, v dot is negative. That's the better way to do that. That's what inspired this, because we spent so much time trying to approximate the manifold. We actually then finally realized, why don't we just pick the manifold? We know what it is, pick it, and then make the states track it. And so that's what we did for this, okay? And the other part is, by doing that, I can take the non-standard form, convert it to standard form. Let me be clear here. We're not inventing particularly the controller that is doing this. That's not what we're doing. We're being able to take the non-standard form, convert it to the standard form, then you can use all those different techniques that people have been doing since the late 1940s and do that. So we're actually enhancing the class of systems they can use. And the other part is to develop as an approach that is independent of the perturbation parameter, independent of epsilon, because you just don't know that. It's very, very difficult. So those are the two big ideas. So the first step in this, and this, I'm going to go just a little fast through this because this gets a little bit tangled up. I wanted to determine the slow control that's going to be as a function of delta 2 to the 0. Those are manifolds. Anything with a 0 subscript will be manifolds. Those are the references that it's going to be going to. And I'll get the 0, the fast state manifold, then to stabilize the slow subsystem. Okay. Second step, I'll determine from that. I'll use that manifold, and then with also Z, the fast states manifold, and U2. And notice what I'm doing. I'm using the manifolds then as a control input to do this. So that'll stabilize the fast subsystem about the manifolds. And then you just have to verify interconnection, interaction conditions. What's that doing? That means when I set epsilon equals 0, I have the fast, I have the slow, but I'm violating. I'm doing a violation because remember, in real life, that epsilon does not go to 0. It has some value, like 0.5 or something, actually, usually a lot smaller than that. So when we set that equal to 0 to get a controller, we're fudging it. So this is now making sure that by doing that, I can take care of the spillover, so to speak, that I have from doing this with the slow and the fast state. So that's what it's taking care of. It's taking care of business with that. To do this, you can use any control technique that you want to. We decided to do it using Lyapunov-based methods. Why? Because it goes fast, it's easy, and I can prove stability very, very easily with this. So you're seeing over here with the epsilon equals to 0 and it's showing up as E. There's my slow system right there. So I define a Lyapunov function V. There it is. Design the control to uniformly asymptotically stabilize about it. Okay. The fast subsystem, I'm going to asymptotically stabilize the error between C and the fast states and their manifold. These equations on the left are just exactly the same ones you were shown before. So same thing, I'm defining a Lyapunov function to stabilize it. And then here's the interaction conditions. And that's to, again, take care of everything that we have. So I have the assumption that they're stabilized, the time varying nature of the manifold, and neglecting the singular perturbation quantity that's in there. So when you do this, what you're going to get then is from that, you get this K matrix. It's a big one. And so there you see the theorem, which we have in that paper proved out there. I have a bunch of different gains to be able to pick in there to do that. And there's many. So there's about 16 just for a typical small problem that's in there to do that. But there's my Lyapunov function. There's V dot as a quadratic form, which is, of course, the easiest way to do that. For the computation side, here are the two examples. I'm going to show just number one, how it works. This one, I'm just going to show you the video from this one. I'm not going to show you the whole design procedure because I'm going to do a more detailed one for this. So the first one will be non-standard 2-time scale. It's a benchmark system. I have infinite manifolds. So ESPT does not apply directly. I'll convert to the non-standard form into standard form. The second one is an F18 example for this non-standard, non-linear. I don't know what epsilon is. I want to force the slow states to track a reference. What are the slow states? Those are going to be angle of attack, side slip angle, and UV and W, the body axis angular velocities. And force the manifold to be the fast state reference using two-stage design, and there's no assumptions. I want to say another important thing about this. No linearization. I haven't really said that. We're not linearizing anything. No linear models on this. We're staying nonlinear during the modeling and the synthesis. Okay. So here is the system that's up there. It looks really, really simple and it's kind of suspect up there. X dot is equal to Z minus U. Z dot is equal to X plus U. So I'll do this slow subsystem stabilization, but by designing a manifold, solving for that. The fast subsystem, I'll design the control, and then there's the manifold computation. It's pretty easy. So here's the system that I have, and there's the closed loop version of it. And now what happens then is when epsilon is equal to 0, notice what happens. I still have this. This is in standard form. But where this was non-standard form because it's nonlinear, now I just have minus alpha sub 3 EZ. So there it is. Now it's linear. So that's what you're talking about, using the control to linearize it. Now I can use whatever, basically method that I want. We showed this, that for different values of epsilon, we can solve directly. If I pick alpha equals 1, alpha 3 is equal to 2, I get stability guarantee for all epsilon less than 0.32. And if I go back up here, look at the phase portrait, you see the different values of epsilon, positive eigenvalues, and here, there it is, 0.32. It's still stable there, and there it is. It's going to go neutrally stable right there. For 0.4 and 0.41, it's unstable to do that. Okay, so that's just showing you graphically, and I can compute it. That's epsilon star there. I can compute that just by picking gains. So the good news is I can do a lot of good things. The bad news is it's hard to pick the gains for this. There's no Bodie, no root locus, no Nyquist. You're having to just somewhat ad hoc pick these, but it's very powerful. All I need to know is that epsilon is less than 0.32, and I'm going to be good to go, even if I don't know what it is. So that's another powerful part. Let's hope the video plays. Oh, it is. So I'll play it twice. This is F18 using this technique, pitching up into a vertical climb. It's then going to pitch over. The velocity is going to get very close to stall. It'll be very, very low. Then it'll roll. And then dive, and then do a pullout for this. Okay, and there it is. That is done using this technique, and the neat thing about it is no linear model, no gain scheduling. We're doing this, and the controllers, everything's nonlinear the whole time. So I'm able to do a nonlinear high amplitude maneuver completely nonlinearly. But the problem I'm getting for this, the something that you don't buy for everything, is if I get linear models, I can gain schedule and stitch those all together. They're easy. This is hard. So what I'm getting is a lot of computational overhead to do this too. So I'm paying for it computationally, and the difficulty of synthesis. But the nice thing about it is that I can get a nice working example. So the research roadmap on this, and I'm going to show some of my previous students what parts they did. So here's the whole thing that you see right here where it goes: known system dynamics, uncertain system dynamics. Anchu did known system dynamics and did state feedback with slow state tracking, simultaneous slow state tracking. She did not touch output feedback or uncertain. This book, published by Siam in 2014 that we wrote, is covering the green boxes that are right there. And we're doing, based upon what I'm showing you in this, the second edition of this book is being worked on right now. It'll come out in about 8 months, 9 months or so for that. And it's not going to replace that. It's going to double the size of it because we're going to do the output feedback problem on it. Okay. From the deterministic side again, from looking at this, if I look at the output feedback on the known system part, I can do slow state, fast state, linear combinations of those. Let me tell you why this is hard. When my other students started working on this, we planned this to go in about 3 or 4 months. And the idea was, I'm just going to measure the slow states, use that. I'm going to measure the fast states separately, just do that, and then the combination of those. This was really tough because estimating the slow states on one of these systems is difficult. Just the fast is difficult, and the combined slow and fast is hard. Each one of these turned out to be really hard. Here's a good example about when you submit journal papers or a conference one. We submitted a paper to ACC, American Control Conference. We had then an estimator working on the slow states and one other one estimating the fast states. Submitted it to ACC, paper rejected. Review comments came back, paraphrasing, what a bunch of idiots. You guys should not design an observer or an estimator to be able to estimate the slow states separately and the fast states separately. Put them together. There's no reason to separate it. What a dumb idea, okay? So the next year for ACC, what did we do? We put one estimate, with a lot of work, one estimating all this together, submitted the paper. What do you think ACC came back and said? Rejected. Reviewers came back and said, you idiots, why would you ever think that one estimator could estimate slow and fast? Clearly, those should be separated into two separate ones. This was such a horrible idea. I can't believe you did that. Okay, what do you do? I mean, so what we did is we just didn't submit to ACC for a short period of time. We just got it out of their system, okay? So here's Dupont, and this is now his dissertation work we're talking about. So we're over here for the uncertain system dynamics. I can have state feedback, output feedback, slow state tracking, and simultaneous slow and fast state tracking. So those are the tough ones. Now, if I look at these for the tracking types, and I'll just summarize this. Over there, we did slow tracking on the generic F18, and then slow and fast on the generic F18. That's what I just showed you for that. And that's using a two-stage design, no actuator dynamics, constant throttle. That's why it bled speed so bad when it climbed up. So Dupont and Saha, I call him Dupont, his first name. We did slow and fast generic, but we were able to add throttle as an automatic control and now command velocity as a state. From doing that, loss of airspeed was reduced with only 10% loss with afterburner. And then finally, we did sequential control. We have actuator dynamics realistically accounted for. Throttles a control, velocity is again. What do I mean by this realistically? The earlier work, we had actuator dynamics. They were just there. When we do it this way now each one of them has their own epsilon. So they are themselves properly modeled as a singular perturbation going in for the different time scales. So that's what we're saying. And on this one, now we have a 90-degree left turn, 90-degree right turn, and we're tracking velocity, bank angle, pitch attitude angle, and then heading angle for that. And this is where I'm going to head in to show where that's at. So the slow and fast state tracking with output feedback. The approach is sequential control of online parameter estimation, nonlinear state observation. I'll talk a minute about why we did state observation. We have more unknowns to be estimated, parameters and states for this, and improving boundedness of errors in terms of the timescale parameters. So the solutions are the following. I want to classify the slow states as measured and unmeasured. Two different types. So I'll allow all slow states to be tracked, or kinetic states. So that's U, V, and W, the body axis velocities, and they're measured. The unmeasured states are going to be not tracked, but they have stable dynamics. That's going to be angle of attack and side slip angle. And then an unknown parameter and an unmeasured state do not appear in the same term. Mathematical expediency makes that a lot easier that way. And then the dynamics of the unmeasured states do not have any uncertain parameters themselves. So this is a little bit simplified to keep it nice, but it's still very, very realistic for that. Okay, so the benefits, the actuator dynamics and uncertainties can be accounted for. And I can now have stability, the reduced subsystems, the full order system guaranteed. So the features are, I can do 4 time scales, 2 slow, 2 fast, 2 for slow and fast actuators. I have multiplicative and additive uncertainties. Not all the states are being measured. And by the way, this is pretty realistic. The 2 hardest things to measure on an aircraft are alpha and beta. They're not impossible, but they're not the easiest. They typically will take flow vanes for alpha and beta because they're aerodynamic angles, or you can do estimators and do things. But if you want to directly measure them, they're a little bit more work and they're noisy signals. Okay, so the Pondon likes to call them the products. I like to say that what it results in. We get control laws, update laws for the estimates, nonlinear observer dynamics, stability has been proved, bounds of timescale separation parameters, and large-scale maneuvers of some timescale aircraft. Okay, now to walk you through, here's what this is doing. X dot, you see in the top row, is going to be the measured states. X dot sub U is the unmeasured states. That's what the U is right there. The gamma of X right there, determined in the purple, the darker purple is going to be the additive uncertainty. And then in the control distributions, which are G's, will have multiplicative uncertainty. And you see that there's delta sub S, delta F. So that's fast and slow, or slow and fast actuators right there. Okay, and so then notice I've not put any uncertainty in the unmeasured states, as I said before. The second slowest time scale are the slow actuators. And now that's correct. The sigma should be there. That's very good. Thank you. It finally came through on that one. So there it's slow actuator differential equation is. The second fastest is the epsilon in front of the Z dot. So those are the fast states. Those are going to be the body axis angular velocity components, PQ and R. And then the fastest time scale will be the fast actuators. You see a row in front of that one. And then the things I'm measuring are going to be slow states. That's not exposition. Slow states, fast states, and then another function of slow and fast state, slow actuators, fast actuators, be able to put through. So to stabilize, we're just going to put it into air, model it as air coordinates. And now the stabilization is just, you see right there, just plugging in and doing that. The thing to point out too is I've got x dot r, that's the reference for the slow states, reference for the fast states, reference for the slow actuators, and then reference for the fast actuators. So the x dots, z dot, and delta dots are right there, the important part. For the parameter estimation matrices, the B is going to be the inverse of the inertia matrices, and then S is going to be just the inertia matrices themselves for that. Nothing too intense there for doing that. We set up a composite, the Lyapunov function, and then all I'm doing is representing that in terms of the summations there for the traces to do that. That's just notation. And then I'll do the time derivative of these using the full order and reduced order model dynamics. No, not too big a deal. Here's the part where it gets interesting, and you're wondering, why did we use this method from Dong and Kunert in 2005? This is commonly used in adaptive control. We didn't invent this, we're using it. Here's why. Because when we were using timescale, we were using estimators, using process noise, measurement noise and stuff. The proofs got to be really hard in a hurry. And the proofs were worked on for quite a while. And so another PhD student is now having that to be able to solve. So to make progress on this, we decided that what we're going to do is parameter updates using traditional ways from adaptive control, because this is not work about parameter updating. This is really work about the time scale. So this is just what we're using to be able to get that. So strictly taking it very, very typical out of that. The parameter update laws have two components. One cancels an error term. The second one drives the initial state. This is just shown out to you for letting you see it. The alphas are going to be gains on the vehicle, so traditional feedback gains, and the thetas are going to be the rate on the parameters, how fast they converge and do their thing. So they're all listed out. So the computational part, when I'm saying this is more computationally complex than gain schedule, it's getting complex in a hurry. Okay. So here's what you do. There's going to be 3 of these to go through. They all work the same way. I'll design the manifold of the slow actuator such that slow states reach reference. So estimates of unknown parameters, ignore additive uncertainty. They will show back up later when we have that. So there it is, the reduced order model. And you see the estimates are now showing up. Get a Lyapunov function. I'm just using quadratic form, which is the world's easiest Lyapunov function. Time derivative. Select the manifold of this for the slow actuators. What happened between here and there? One thing. All you're doing is you have it right there. Delta F0, the actuator, the manifold for the fast actuators. I'm just solving for it right there. That's all that is, to go from that whole line to that. Solve for that. Okay. And then stability for that, just to stabilize it. Design the slow control using exactly the same approach, using the reduced order model. That's right there, doing the exact same thing. You're solving for U sub S in this case. There it is right there to be able to do that. And then manifold of the fast actuators. You're just going after delta F0 again, and then doing stability for that. So same thing. And then finally, the fast control, again, the same thing to do that. This is pretty standard. The composite Lyapunov function is looking like this. And now here's the question, where does the observer come from, since we're not using process noise and measured noise to estimate? I'm adding this term on here, this x tilde, so unmeasured. So these are the unmeasured states after errors on it. And now this is what I'm going to use to be able to derive the observer. It's going to come directly from this. Here's the composite Lyapunov function using, again, summations instead of the traces on there for doing that. And then I finally get to selection the observer dynamics. So here it is. There it is by taking v dot sub c, and now here it is on the bottom. So this is where the observer is going to come from. So this is going to be x hat dot of u. That's it right there. I'm going to solve for that. Everything else will be on the other side. So this is where the observer comes from. So from that, I'm going to have a term that'll cancel in v dot c. I have a term that'll cancel in v dot c in the middle right there. This is just going to be traditional, like Limburger observer. So there it is, observer gain, x hat u minus x u. And then the middle term, which is called mimicking on there for just whatever term you use it. There's x hat u. So there it is. This is traditional. I'm canceling and then mimicking with that. And then finally, I can just, it's just showing to get ultimate boundedness, I can just choose L diagonal on that. So here's the example to show you where this is all going. I'm going to show you 3 different controllers. I'm only going to develop, we developed number 3. I'm not going to show you 1 and 2. Number one is slow state tracking with full state feedback. So all the states are assumed fed back. Number two, slow state tracking with output feedback, like we just did. And then similar, but then number three is simultaneous slow and fast tracking with output feedback. So the vehicle is going to be nonlinear 6-stop at time constants. There's the velocity is 800 feet per second at 15K. So it's a nice, for the F-16, that's a nice, good flight condition right there. We'll pitch up to 80 degrees in 10 seconds, hold 80 degrees for 10 seconds, return to nose level in 10 seconds, fly level for 10, 90-degree left turn, followed by 90-degree right turn, 15 seconds return. Bank angle of pitch or commanded to 0 upon completion of the turn. You get 180 seconds to do that. And as we're saying, we're not measuring alpha and beta, but just measuring body active velocities. The sources of uncertainty put this in are, of course, to be this way. This will have a big impact on the results. So for the inertias, I'm going to set those initially at 15% value. The actual estimates meter will be 5% above. Controlled derivatives, not the stability derivatives, but the controlled derivatives are the hardest ones to get. They're going to be 50% below, 50% to start, 50% above is where they're actually going to need to go. And the engine time constant to be modeled there. So we're really throwing all the estimates off for the inertias and the stability derivatives and the control derivatives for this. The gains and perturbations. So by designing the controllers, you see the Ks that are on there. So all the different Ks, and those are picked, a lot of that through trial and error. The online parameter estimator, they're the alphas. Some of them are very small, 10 to the minus 13, 10 to the minus 15. And then these are for the parameter updates. Those are the rates, basically the thetas that are going on there. The observer gain is gigantic, as you see, 5,000 and then 10,000 on that. And the perturbations, we've added perturbations on these. These are a bit on the cheap side. So this is just going to be a sinusoid of 10 radian per second that's on it. So we're giving it that perturbation rather than giving it something stochastic like driving turbulence or anything for that. So here's what it looks like for the trajectory. You're getting to see downrange, so it's going that way. Cross range to the right, so it goes, pitches up, left turn, levels, and turns around. And you're getting to see the commands there. So reference C1, C2, C3. Green was the one we just looked at. They're very, very similar in many things. So if you're looking at this and wondering, what's the point? What does this show you? Consider what's being shown. C1, the one that's in red, has full state feedback, perfect measurements. It's all there. So that's the thing. I want to match that one. I'm really hoping that blue, but especially green. I want green to match red as much as I can, because that's, again, the harder case that I have. So where you're seeing they're going to be different is over there, and that one's going to be beta. So there's the side slip angle beta. It's got some differences in it. And the controls are very, very nearly the same for here. And I'll talk about why that's going on in just a second. So the trajectories, you're getting to see those right here. Bank angle, pitch attitude angle, and heading angle that are down there. And then P, Q, and R, the body axis angular velocities. The reason these are different is consider what's going on. When I'm doing slow state references back to here, C1 is slow state tracking. That's alpha and beta. The fast state tracking is going to be P, Q, and R. Number 3 is alpha and beta and P, Q, and R. So you're getting to have everything combined. So this one compared to the red, the reason you're seeing it's different is I can now command P, Q, and R directly. The red one can't. It's just commanding alpha and beta. All right. So that's why there's differences. This is just showing the uncertain parameters. Everything converges. Everything is nice. That's all you're seeing. I get a little bit of, bubbles in the B's, but they come out. Same thing for down there. Here's the final controller comparison before we get to conclusions now. So if I look at these C1, C2, and C3, you can see full state feedback, output feedback on alpha hat, beta hat, and then alpha hat and beta hat. States to track, slow and fast. The number of turning knobs, let's say whatever it happens to be for N, and the dimension of the system, more turning knobs, smaller, less. But whatever you have for, you want to call that N, this will be NP3, N plus 3, this is N minus 1. So during the full state, I have less design knobs I have to fool with to be able to do that. This did a climbing turn, this did a climbing turn, this did a level turn, close to level turn. This is what you wanted it to do. This one now had more controls. I could modulate pitch rate directly on this. Those two cannot modulate pitch rate. They're not able to do that. So pitch rate, I can modulate that control to be nose down. The velocity over Q was higher, a little bit higher, but it's still subsonic. It didn't go supersonic when it did that. compared to the baseline. No major change in heading. The throttle energy, 6% less using this, but the aileron, 41% saving, 40% saving, more and more. So the answer is, which is the better? Depends what you want to do. If I want to be able to do awesome maneuvers and not be able to measure alpha and beta and to be able to command PQ and R, have a more sophisticated controller, I'm going to use more control energy. That's as simple as that. If I have not quite as good performance, it kind of balloons and climbs in the turn and everything. Yeah, I'm going to be using controls a lot less because these two controllers are not as aggressive. They're not able to do more. When I added the faster time scale variables, the fast things, I have to use more controls to mess with those. So that's really all this is saying. I'm doing a lot more with that, takes a lot more control use. So which one's best? It's up to you. So the summary and conclusions then for this, we've accounted for slow and fast actuator dynamics of this, additive and multiplicative uncertainties, absence of full state feedback, the parameter update laws and simulation, two sets of gains were chosen ordered by several different orders of magnitude. And so the estimates could be used effectively and it worked really well. We did that on purpose. But I will say also, this is bringing me to mind, the gain on the controller number 3 was extremely aggressive on the throttle. And that's what partly was causing the velocity overshoot for that too. We have new bounds of the timescale separation parameters. I didn't show those. So those are now sigma hat, rho hat, and delta hat. When I have those, that's just saying, here's the upper bound for stability. On those, I can say, as long as the parameter that I have, that timescale parameter is below that, I'm going to have a stable system to be able to do that. So I have new bounds that I did for that. And use of compact sets and the extreme value theorem were just used to alleviate differentiation of the manifolds. Okay. The control estimation laws were adequate to achieve a good simultaneous and slow fast tracking, even when the initial estimates were off by 50%. And the output feedback control led to estimated states being close to actual time. Okay, so where's this going after this? Naturally, I want to account for exogenous inputs and do it stochastic rather than deterministic form. So an unset to common filter or ENKF, I'll use stochastic Lyapunov functions, probably is where that's going to go. The unmeasured fast states in addition to unmeasured slow states. Remember, we just assumed that alpha hat and beta hat. I didn't say anything about the fast states being unmeasured. This was just the slow ones only. So the slow observer estimates that in the slow time scale fast. So we're going to go back to that even after having our hand slapped or face punched or whatever you want to say about from ACC. So we're going back to that. The sample data controller for that. So Chris Leshikar, that's his dissertation topic, is to go single rate and multi-rate with this, and then add in uncertain dynamics in that. So uncertainty in the structure of the dynamics. We had parameter uncertainty of inertias and things. Now we're going to go after the structure of the dynamics being uncertain. So that's his dissertation. And then Cameron Eves, who's going to be defending in early spring, probably by February, he's been looking at adaptive control for multiple timescale systems to account for this. And for a while, people were saying that that was a difficult thing to do. You almost couldn't do it, but he's got really good results. There's SciTech, ACC, the CDT papers going on in this. There's a lot of work now. He's got that going. So there's our future work on this and the people that are doing it. Lots of pubs. I can send those to you. And these are the sponsors. It started out from AFOSR. They went to NASA headquarters for UREDI, NSF. Person with an NSF fellowship worked on it, DOD NDSEG fellowships, and then the undergraduate summer research grant for that. Okay. I made it.
Questions? All right, Karen,
Yes.
hold.
No, great talk.
Thank you.
So you mentioned when you had to design the Lyapunov function, that you said like you just kind of chose one that you wanted and kind of made it work. But I mean, the feeling I get is generally hard to come up with a Lyapunov function and finding you have more insights into that and how do you make sure like the code trace were.
Exactly. So let me go back, because when we said it was in the early one, like that second order system and the early things, we were just picking those to do that. Once we got to this, now we're going composite Lyapunov function. So now it mattered. See what I'm saying? So for on this, I've got V1, V2, V3, V4, and then I have the trace of the B matrices and then the gamma matrices. This is long. So early on, yeah, you can use anything you want, but to get where we needed to go for this, we're using composite. And I will say that a lot of that reason also to go at was to get this, we needed to get an observer. So by putting this in to get the observer, that's where we went. So this part definitely was not ad hoc. This was very, very carefully planned out to get that. That took a lot of work, yeah. I'm still, none of us are happy about this. We've just had to do that for expediency. It worked. I personally don't care if it's an observer. Some people really don't like those. And so some people have thrown fairly good sized rocks at us for using an observer instead of using an estimator. But it works. It's a nonlinear observer, so. Great question. Yes.
You said the controller gains in this one. I said kind of trial and error type setup. So can there be like just optimization of maybe again?
Oh, great idea. So yes, we did not do anything to optimize the gains at all. Those were picked. And so we were just picking unity for all of them and then having to adjust them as we went. And if you're wondering how long that takes, and so as a PhD student, you know, Dipanjan, how long did that take and everything, or how's that going and everything? Well, I'm halfway there. So it would take about a week to be able to pick those, to be able to do that. But spending for the student spending a lot of time. But yeah, another technique to help pick those would be nice, but welcome to nonlinear control. That's what we're giving up by getting away from a linear system, all these other nice methods where linearity, superposition and homogeneity exist to be able to do things nicely. Yeah, it's just a bit of trial and error. And I will say that I can't really say that I'm not going to say that any of this is optimal or in super duper or anything like that. Because we're picking these, we want to be able to pick these controllers and compare them. So a lot of work was to get them good, but we did not spend weeks and weeks trying to get little tiny changes to get them optimal. I wanted to be able to compare them, everything. But that's one of the limitations. I would say one of the hard parts of this method is it's not easy to do this. It takes a lot of work to design the controller. But compared to the early versions where we were estimating the manifold, that was bad. That was really, really bad to be able to do this. This is a lot better. Once we decided to pick the manifold, which we should have done early on, life got better. If you had asked me what would I have done different, knowing what I know now, I would have said forget estimating or approximating the manifold, pick it. Don't know why it took us so long to figure that out.
Well, hindsight being 2020.
We were both working on it. We're just attacking it. And the harder it got, we're just like, I'm going to stick with this and do it. We should have just said, there's got to be a better way.
Were you going to give a question?
Yeah, I was wondering, are there any situations where it's better not to model this fast, like as time is scale and just treat them as disturbances?
Yeah, exactly. So if what he's saying is there a situation where it's better not to model them as fast and slow? Not modeling them as fast and slow is what's done in 99% of the cases right now. So just aircraft example. Use the short period approximation, use the cuboid approximation. You're not going to model it as fast and slow. You're just going to separate out the two modes and design a controller for this one, design a controller for that one, and just put them back together. And so if I'm talking about this to industry and things like that, they're going to say, we don't need to do this. We've been doing this since the 1950s. We just design, you know, for whatever that mode, and just do that. We don't need this. My response is, I agree, but this is all nonlinear, and I'm not gain scheduling. I'm going to get a controller that is not just doing that. So there's some nice advantages. I can do full amplitude nonlinear stuff without having to do this. So yeah, there's a workaround that's easier, but if I'm willing to put the time and investment into it, this has some nice properties. And as a research problem, it's fascinating. I really like it. I like this one a lot.
I don't have any
Other questions? Yeah.
I just wanted to point out, I remember a nice talk on sort of neuron cells having fast and slow dynamics. I was wondering if you could somehow connect to those areas too or not.
Potentially, definitely. One thing that had been talked about earlier was enzyme kinematics. I did not like those. My co-op, one of my students spent time doing that. Plasma is another one that you could be done with this. There's so many that could be done if you can do the modeling. I will say again on this is also assuming you're very good at modeling and you can get a model of the system. If you can't model the system well at all, you can't do this. But we're also heading toward that. As I said, Chris Leshkar will be doing modeling now where not just the parameters are uncertain, but the formula of the equations is uncertain. You know, it's good. You don't know that well. I don't know where that's going to go exactly yet. But yeah, any plasma, enzyme kinematics, there's so many different lasers, you know, a bunch of areas where I don't do work, but people are saying, oh yeah, we could do